Alrighty, guys. Good afternoon. Good morning. I don't know why I keep saying afternoon today. Today's going to be a fun day. William's going to teach us about mins and maxes, section 4.1 in the textbook. I'm also waiting right now to see, we're expecting Asha Brunnings to come in today and talk to us a little bit about the Brain Bowl team. I sent her the link for our Zoom meeting, but just a minute or two ago. So let's see if she manages to make it in. There she is. Hey, Asha. So we'll give just a minute or two for other folks to show up. I think we're still missing 3 or 4 people. Maybe while we do that, I'll grab some coffee. I'll be
Sure,
right back.
coffee sounds good.
We can get started here. Okay. Well, it looks like we're a little bit light today.
I'm in no rush, but
okay. Yeah, we can hang out just a minute or two longer. That'll give William some time to get all of his materials prepared. I did get an email from Tesha saying that she's out of town and may not be able to make it today. But we're missing Sarah also. Yeah, we can hang out just a minute or two more. I didn't get any other emails saying folks wouldn't be here, so hopefully a few more show up.
So how's the math team doing this year? Are they active?
It's not especially active right now. I have 2 students from last year that were working on kind of independent projects. One of them is close to publishing a paper. That's really exciting.
Oh, cool.
And the other one is working on training up for the integration bee at UF. But because we haven't been able to have in-person meetings, the kind of structure of the team has been a little bit weak. And unfortunately, the Math Olympics is still canceled. They've been for the last couple of years, which has been really disappointing because that was our main event. But that next spring they'll bring it back. So I haven't heard from the folks whether or not they're going to be doing a 2022 Math Olympics, but I've got my fingers tightly crossed that if everybody
yeah, so Alejandro actually was on my team and he always competed in the integration bees.
Wonderful.
He loved integration. That was like his thing.
He's very good at it too. I remember he was actually the impetus for us to start a separate math team group just to train for the integration bee. And he ran that for me almost completely independently for about a year.
Yeah, he was an excellent Brain Bowl player last year. I actually had 2 team players in the top 5 of the state championship, which is unheard of in the individual. So I think Matt came in first and Alejandro was 3rd or 4th in the individual scores. So we were unbeatable last year.
That's wonderful.
And of course, they all transferred now and left me.
Yeah, it's sad how that happens, isn't it? You know, we get to work with them and build these relationships, and then they move on to bigger and better things. Always happy to see that, but also always a little bit sad.
It is, but yeah, so it means we need to keep on recruiting and bursting into classes like this.
Absolutely. All right. Tesha, I know is not going to be here today. It looks like Sarah probably isn't going to make it, so let's go ahead and get started.
Okay, so good morning, everyone. My name is Asha Brunnings, and I'm the coach of the College Brain Bowl team, also known as Quiz Bowl. Has anybody heard of Quiz Bowl before? Like, I can't see your faces because everybody has their camera on, but you know, you got to raise your hand.
I have not.
You have not. Okay. So Brain Bowl is an academic quiz tournament. Are you familiar with Jeopardy? This is kind of like Jeopardy on steroids. So you would compete in a team with 4 people. And normally when we do face-to-face tournaments, everyone has a buzzer, kind of like Jeopardy. And you would buzz in and There's toss-up questions. If you buzz in and you get it right, you get 10 points. And then you get 3 bonus questions that you can talk to each other as a team and answer. So the toss-up questions are individual. The 3 bonus questions are team effort. And in the spring, we compete in the state championship, which has a quarter of all the questions are computational math questions. And so usually most teams don't have a very good math continent, but as because I'm in the sciences myself and I can teach a little bit of math myself, my teams have always been fairly good in math. But this year we're a little short on math people, so we could really use some people. But the other questions are on literature and history and geography and politics and even popular culture. We call those trash questions. And there's always some trash questions in packets. We have a tournament coming up on Saturday, actually, and a practice tournament this evening. So if this is something you're interested in, I'm going to put my email and our Discord channel link in the chat. And you can send me an email or you can join us on Discord. But as an example of what it's like, I want to give you like one toss-up question to sort of give you an idea of what it's like. Now, a toss-up question for math, it gives you the problem that you need to solve in the very first sentence, right? And then it goes on to explain how you would solve that. Now, if you know how to solve it, you ignore all the explanation and you just work on your piece of paper, because once I'm done reading, you will have 6 seconds to answer, to buzz in and answer, okay? So I'm going to read a toss-up now, toss-up number 1. Bob needs to find the first derivative of 2x times cosine of x. He remembers he must use the product rule. He recalls that if he takes the derivative of the first term, writes down the second term, and then reverses the process, he will be able to compute for 10 points the derivative of 2x times the cosine of x. So who can do that? Oh, what's happening? So you need to, if you know the answer to this, you need to buzz in and say buzz, or raise your hand, or better yet, turn on your camera and say, yes, okay, what's it?
Is it 2 cosine x minus 2x times sine x?
Yes, that's correct. And I wouldn't care about the order of this. So you could just say minus 2x sine of x plus 2 cosine x. So yes, that's correct. Good job. You should join our team. So now all together, you guys can talk about this. I'll give you some bonus questions for 10 points each. Determine the following limits. The limit as x approaches 2 of the quantity x squared plus 2x minus 8 all over x minus 2.
Could you repeat again?
I can. Normally in a tournament, I cannot repeat it, but you'll get used to listening to this, okay? So the limit of x as x approaches 2 of x squared plus 2x minus 8 all over x minus 2.
Oh, we got it in chat there.
Oh, Nikita, nice try, but that's incorrect. You need to try factoring the top. So x squared plus 2x minus 8. Try to factor that.
I believe she's correct. The limit is as
Is
x
she?
tends to 2. Yeah, that would be 6.
X squared plus 2x minus 8?
Yeah,
because my answer
2 times
is it
x plus
6?
4. Yeah.
So she's right?
She is, yes.
Oh, look at that. Well, thank you, Nikita. I guess sometimes these answers are incorrect and I just randomly picked a question. Okay, so I'll give you one more. The limit as x goes to 0 of x squared divided by 1 minus cosine squared of x. I'm going to repeat it.
Trickier.
Okay. So the limit as x approaches 0 of x squared divided by 1 minus the cosine squared of x.
This is a good one.
No, there are lots of good ones. And if you want to help like proofread some of these questions.
I'd be happy to.
Nikita, you can do this. I have faith in you.
Yeah, you guys can
pressure.
do this.
Okay, so nobody comes up with this. John, did you want to take this?
Sure.
All right.
Here, let me. So if you guys remember, right, sorry, this is just me scribbling, but yeah, that numerator factor is like this, and then you cancel the x minus 2s, it's the previous one.
Yeah.
You still got your limit x to 2 here, so you'd have 2 plus 4 is 6. This guy is 1, and the trick, guys, is one of those special trig limits. So remember, x over sine x, just like sine x over x, goes to 1 as x goes to 0. And what we have here is the square of that ratio. So this limit would be 1 squared, which is 1.
Yep, correct.
So we're leaning here on that sine x over x limit. That's really what we're doing. If we
Correct.
want the other details, we would say this is lim x to 0 sine x over x all to the negative 2. And that might make it a little easier to see because the sine x over x limit is one that we've worked with previously.
Yeah, so see, that's correct. So a lot of this math questions is not so much being able to do long complicated calculations, but sort of seeing the patterns, because all of these questions are answerable within 5 to 6 seconds after the question is read. Anyhow, I don't want to hold you up, but I put it in the chat. I'll put it again. Here is my contact information. If you want to join our team, we have like a play tournament tonight at 7. So if you want to try it out, you can just come and hang out with us and not participate and just observe. That's fine. We have our first tournament on Saturday. Again, it's not a very serious tournament. Serious tournaments don't start until January, but I want to recruit now so that I can get you ready for that. We have 3 sort of fun tournaments this semester that are mainly for like bragging rights more than like for championships. And so, so thank you so much, John, for letting me pop in here.
Yes,
I
yes,
hope
I'm
that
sorry
I get.
it took so long to get
Oh,
this
no
together.
problem.
And
Yeah,
guys, I've went ahead and made an announcement in Canvas that has the contact info and stuff that you need to get a hold of her in case you lose it from the chat here. If you enjoy this sort of thing, I think it can be a lot of fun. It's a good way to flex your math muscles and get a little bit of fame in the community, and also just meet people like-minded and experience the world of competitive academics, which is a cool world. It's a nice place. So
right.
please consider joining the team and reach out to Asha if that sounds at all fun to you. And then I guess with that, we'll go ahead and get started with class for the day.
Okay. Yeah. Bye-bye.
Okay, thank you. All right. So yeah, for those of you who came in a little bit late, that's the coach of Santa Fe's Brain Bowl team. She's been reaching out to me asking if she can come here and try to recruit some of you to the team. One of my old students, Alejandro, was previously on the Brain Bowl team, and he came in 3rd nationally last year. Which is a big deal. And there's prize money and other good stuff associated with doing extremely well as they did. We also had another student come in 1st nationally last year. He was not a previous student of mine, at least not to my knowledge. But I'd like to strongly encourage you guys to try out, talk to Asha and see if that's something that you would enjoy doing. I have no idea. That's a good question. I am not directly involved with the Brain Bowl, so I don't know when their tournaments are. But that would be a good question for her, for Asha. So I did go ahead and post an announcement here with the info that you need, her name, Brain Bowl, blah, 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 email, and the Discord. And I'm sure if you join this Discord server or shoot her an email, you can get all of those questions answered in good time. All righty. Scholarships are out there too. That's very nice. Scholarship money is always a nice thing. So with that, let's go ahead and get ready to get started here. Today is William's Student Teaching Day, and he's going to walk us through section 4.1, which is on finding mins and maxes for functions using derivatives.
And also, actually, on that note, could you please give me screen share permissions?
Yes, sir. Let me go ahead and make you a co-host, and then I will hand things over to you. All right, you are now a co-host.
All righty, share desktop, just screen. All righty, wrong thing. So first off, beginning. We will be going over the relative and absolute extrema of section 4.1. Now, we will start by going over some definitions. We'll then be going over specific examples of said definitions, and then we'll go on from there. So first off are the relatives. You have the relative mins, which is the smallest point in a local area. This is different from absolute mins, which is the smallest value of the function over its entire area. For instance, if you look at the graph to the right, section number A is an absolute min, as it is the lowest point over the entire graph, and number C is a relative min, and it is the lowest point in that area. Same for relative maxes and absolute maxes. One thing to keep in mind is that absolute maxes can be relative maxes as well. Relative maxes might not necessarily be absolute maxes, as shown with B and D. Another thing to keep in mind, as for cases with such as cosine x, is that there can be more than one absolute maximum. As the absolute maximum just means the largest or smallest point on that entire graph. If it has a repeat, it is also in addition to an absolute maximum or an absolute minimum.
This is really good, William. Could I ask you just, Sarah mentioned something in chat, and I agree. Let's run back through those slides and just talk a little bit more about each and give people time to draw the pictures and get things into their notes, because it takes a little while to write this stuff down. So these are really great slides. I like them a lot. Let's just hold for a minute on each of them so people can fill in their notes.
Yep.
And maybe while we're waiting, I'll talk a little bit about the vocabulary. So absolute min and absolute max, like William said, are the lowest value on the graph and the highest value on the graph. So those are so named because they're the absolute maximum output, or largest y value, and absolute minimum output, smallest y value. Another term for relative min or relative max is local min or local max. So a relative max or a local max is going to be a place where when you zoom in on that graph, it's the tallest point anywhere in that window that you zoom in on, or kind of the tallest point nearby. They tend to be tops of hills. Local or relative minima tend to be the bottoms of valleys, although not necessarily. If your function isn't continuous, things can be a little bit weird. But that's the idea, and those are the correct definitions. And this picture here is a great way to get a feel for that.
As I give just a bit more time for everybody to write down stuff.
And I like what William said about absolute maxes sometimes also being relative maxes, and absolute mins sometimes also being relative mins. Those can overlap. And if you look at the strict definition of an absolute max and a relative max, or an absolute min and a relative min, it is the case that an absolute max is always a relative max. And it is the case that an absolute min is always a relative min. But as you work the homework problems, pay careful attention to the wording, because sometimes when they ask you to look for local or relative maxes and mins, they'll say to ignore the endpoints. The endpoints can definitely be an absolute max or an absolute min. And if we're interpreting the definition carefully, they're also always relative maxes and mins. But sometimes the homework asks you to exclude endpoints from your set of relative maxes and relative mins, because you want to have stuff on both sides to compare to.
Now, specific example, we've gone over the fact that there can be more than one local and absolute maximum. Another thing to be concerned about is stuff with no absolute maximum or no absolute minimum. In the case of, for instance, y equals x, which is just a straight line going from negative infinity to infinity with a range of negative infinity to infinity, has no extrema, as it has no absolute max or absolute minimum, as it in itself is infinite without limits. And as such, it has no defined points where it ends. Now, with that in mind, y equals x with a range of -3 to 6, or with a range of any number, or any real number, has an absolute max and an absolute min, simply because it has endpoints. It has points where it is absolutely the max and absolutely the min.
If you don't mind here, I'd like to pause for a second and share a graph. Just
I was
to
actually
help.
just about to do that, which is
Okay,
this.
very good, very good.
Case in point with this graph right here, it has a hole at 0 and a vertical asymptote at 2. This has no absolute min or absolute max. And that's because in this case, it gets infinitely close to 0 without actually hitting 0. So there's always a point where we can always get slightly smaller, slightly smaller. In this case, it has an absolute limit, it has a vertical asymptote at 2. Infinitely close to 2 without ever actually reaching 2. As such a
And if I could, let's take a quick look at the graph of the example you used before with y equals x. I think it would be nice for folks to get that in their notes, and I can pull that up here. So I'm going to steal your screen share for just a second, sorry. So if we look at y equals x with no domain restriction, that's the graph up top, this guy with these arrows continuing on and on forever, he definitely has no maxes or mins. There are no tops of hills here, there are no bottoms of valleys here, and because these arrows indicate that the graph continues going on and on and on in both directions, there is no largest y value on the graph, and there is no smallest y value on the graph. But like William said, if you restrict the domain to a closed interval from -2 to +3, now there is a tallest point on the graph, and now there is a lowest point on the graph. So this would be an absolute max, and this would be an absolute min. And just a quick touch on the terminology here, we would say there's an absolute max at x equals 3, and the max value is the y value there, which is also 3. Because we're on the graph y equals x, this point is 3, 3. Similarly, down here, we would say there's an absolute min at x equals -2, and the min value is the y value there, -2. So when we talk about where is the max or where is the min, we're talking about the x value. And when we ask what is the max or what is the min, we're talking about the y value. So when we say max value, we mean that's the largest output or the largest y value. And when we say min value, we're talking about the smallest output or smallest y value. And then you can tell me where they are by giving me the x values. So that little bit of vocab can be another sticking point on problems. We tend to want to give these things as ordered pairs, like this point is the max. But the vocab can be a little weird. Sometimes we ask, where is the max? And the answer there would be, well, the max is at x equals 3. Or what is the min? And what is the min would be the y value here, which is -2. So this is a good example of how it's not just the algebra of the function, it's also the domain that determines the absolute extrema.
Question.
I'll hand it back over.
I just had a quick question on that one.
Sure,
That second
yeah.
example there. Would if you also make it on that interval there, would that also be like a local max and a local min?
This is a good question. So if you look at the strict definition of a local max would be, if you zoom in here, if you look just in this window, is that the largest point in that window? The answer there is yes. So technically this would also be a local max, and technically this would also be a local min. It's an unfortunate fact that your textbook sometimes considers endpoints local extrema and sometimes does not. But if you're asking, as a mathematician, what is the correct answer here? The correct answer is that this is also a relative max. And this is also a relative min. And remember, relative and local mean the same thing. So yeah, this would technically be a local or relative and absolute minimum. And this would technically be a local or relative and absolute maximum. But your textbook sometimes conflates those, sometimes doesn't want you to do that when these things are endpoints. So for the purposes of homework, read the question carefully. If it says don't include endpoints, for your local maxes, then you wouldn't call this a local max. But the actually correct answer here is that yes, absolute extrema, so a neat fact, every absolute extrema is the word for min or max, is also relative. However, not all relative extrema are absolute. So anytime you find an absolute max or an absolute min, it's also a local max or local min. But there are plenty of relative maxes and mins that are not absolute.
Relative extreme is same means the local max and the local min.
Yeah, the word relative means the same as local. So relative and local mean the same. The other kind of pair of words, we use absolute, but the other term is global. So an absolute max is the same as a global max, and a relative min or max is the same as a local min or max. So absolute and global mean the same thing. Relative and local mean the same thing. They're just two words for each of those that happen to mean the same thing.
In the book, the local max and the local min, it cannot be an endpoint because it talk about both sides from the point left side and the right side.
Right.
When they X is approach to the maybe C point, and if it's an endpoint, the other side it doesn't have anything.
So it's true that when we talk about a local min or a local max, it's nice to be able to talk about coming in from either side. But if you look at the definition, this definition is definitely satisfied by endpoints. So here, for example, f of 3 is 3. And if I look nearby at any x value nearby 3, the y value on the graph will be smaller than it is at 3. So this definition is satisfied by endpoints. Now they get a little, like I said, they do get a little bit picky about endpoints, but technically endpoints can be local mins and local maxes. So it's there isn't any reason why we cannot call these endpoints local maxes and local mins just based on the definition. But you're right, Yuping, in that the way we're going to be hunting for local mins and local maxes in general will involve derivatives. And a function cannot be differentiable at this endpoint because we can't talk about a limit coming in from the right. So that's why they do that. But I do think it's first off, it is a fact. It's not an opinion. It is a fact that every absolute extrema is also relative. But the way we tend to look for them, it's kind of nicer if you choose to think about these as not being endpoints. And that's why your homework does what it does, where they sometimes exclude endpoints. But I'm not aware of any important way of looking at this that says an endpoint can't be a local max or a local min. They certainly can be. So if you were to tell me on a test that this is both an absolute and local max, I would say you're 100% correct. But be aware that in the homework, they will sometimes ask you to exclude endpoints. All righty.
All righty. All righty. Moving on just a bit. Come back to the way of how we actually find maxes and relative mins and absolute maxes, absolute mins, is derivative test. So first off, let's take x squared as a function. And as we all know, x squared, first derivative of that is 2x. So if f prime of x is greater than 0 on an interval, then it's increasing. This is pretty common knowledge. We all know this. And if it's less than 0, it's decreasing on the interval. Now, when f prime of x changes from positive to negative, a relative maximum is made, since a peak is formed. It goes from an increasing function to a decreasing function. And same way, when f prime changes from negative to positive, such as in x squared at 0, a relative minimum is made as it makes a valley. Yeah.
This is
That's
good.
all.
If you don't mind, I'd like to insert another picture here just so folks have these in their notes.
Yeah, go right ahead.
So going from just draw a nice general shape here. We've got something like this and then something like this. It is a fact that if f primed of x is greater than 0 on an interval I, then f is increasing on that interval I. And if f primed is negative on an interval I, then f is decreasing on I. This is not something that we've seen formally yet, but it is true, because if your derivative is positive, then the slope of your tangent line is positive, and that means you're going uphill. If your derivative is negative, then your tangent line is sloped negatively, so it means you're going downhill. And you can kind of imagine, just like William was saying, if you transition from being decreasing to increasing, then you've got to have rolled through a valley. So we are decreasing over here, increasing in here, and decreasing here. So this is the graph y equals f of x. Maybe I'll just call these numbers a and b. And if we look at the derivative, my tangent lines are all negatively sloped here, positively sloped here, and then negatively sloped here. So my derivative has to look something like this: negative, 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 and then 0. And now here, my function is increasing, so my derivative would be positive, 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 positive. And then when we get to b, we switch back to being decreasing, so my derivative has to be negative again. So this could be a graph of f primed. So where f is decreasing, f primed is negative. Where f is increasing, f primed is positive. And then f is decreasing again here, so f primed is negative. So you can hunt for these guys, the mins and maxes, by looking for places where you transition from decreasing to increasing, or from increasing to decreasing. And those will be places where your derivative is perhaps equal to 0, but definitely changes sign. And that's the first derivative test that William was just saying. So if f prime changes sign at some x value, then that x value might be a min or a max. And this is kind of the picture that goes along with it. All right, coming back to it.
Mm-hmm. I was about to show that, but
I'm sorry.
yeah, so that's good. So, and then another thing, so we've talked about the first derivative test. Now we need to talk about points of inflection. If in a position velocity acceleration, the first derivative is your velocity, the second derivative is your acceleration, the changes instead of velocity. And the point of inflection is when, if you can imagine it, is when the tangent lines for this graph actually intersects and then actually swaps over onto the other side. Best way to explain this, I believe, is with how is that actually? Take x cubed, for instance. There's actually a point in inflection at x cubed at x equals 0. And that is when you take the second derivative of that, so 3x squared, and then 6x is when the second derivative intersects 0. It goes from negative to positive. As with first derivative, when f double prime changes from positive to negative, a point inflection is made, changing the formula from concave up to concave down. And when f double prime changes from negative to positive, when the acceleration changes from negative to positive, a point inflection is made, changing the formula from concave down to concave up. Yeah, it's a point of inflections are a bit more tricky, but just think of it as essentially the first derivative test, and it's pretty simple. And then last thing that we really have to go over before I'm just going to be showing you a host of examples to go with all of this is critical points. Critical points are essentially your extrema is whenever a function is either 0 or undefined. So it is your vertical asymptotes, your holes, and also your relative maxes and relative mins and absolute maxes and absolute mins. Is where, except at endpoints in that case, in that circumstance, is where the derivative function is either 0 or undefined. Actually, no, that includes the endpoints. Never mind. Yeah. Just do something quickly. So yeah.
Real fast. Before
Yes.
you do the examples, could you go back to the second derivative test? I wasn't able to finish writing that stuff down.
Yes, of course.
And thank you. This is all really, really cool.
Mm-hmm.
I still cannot understand here.
Which part?
When f second prime changes from positive to negative, a POI is made, changing the formula from concave up to concave down.
Yes.
I cannot understand this part.
So actually, I'm going to go back to so point of inflection is essentially this bit right here. It is when that changes. Now, concave up and concave down refers to the actual line and the way and the direction is heading. And concave up is the direction is heading. So as x moves forward to the right, this will be changing. So it'll be heading towards. So it has a positive acceleration. So it'll eventually be heading towards a positive value. Eventually, inflection point is a change from either concave up or concave down to the other side. Whereas concave down, when you move more to the right, the acceleration decreases and the velocity decreases, and then the position decreases.
Can I say that inflection point is a critical point?
So an inflection point can be a critical number. It's possible that both the first and second derivative would be 0 at an inflection point, and x cubed is an example of that, but not always. Sometimes inflection points will be critical numbers, and sometimes they will not. Have we defined what a critical number is yet? Here we go. Yeah, so a critical number is a number in the domain of the original function where the derivative f prime is either 0 or undefined. We will talk more about inflection points in the next section, but the main point of the second derivative test, I may share just a quick picture here. The main point of the second derivative test so let's talk briefly about concavity. So concave up graphs, these look like this, right? They would hold water if you poured water in, and concave down looks like this. So you can be decreasing in concave up or increasing in concave up. You can be increasing in concave down or decreasing in concave down. And the big deal behind the second derivative test is that if f primed of c is equal to 0 and f is concave up at x equals c, that means you're looking at something like this. So if you're concave up and you have a horizontal tangent line, meaning the first derivative is 0, then that has to be a local min, because you have this sort of shape, you're concave up, and you have a horizontal tangent line. And there is a local min at x equals c. And the way to tell that you are concave up is to look at your second derivative. Being concave up at c means f double primed of c is positive. And then the other version of this is if f primed of c is equal to 0 and f is concave down at x equals c, then there is a local max at x equals c. So if you are concave down and you have a horizontal tangent line, then that has to be a local max. So the horizontal tangent line is the f primed of c equals 0, and the concave down here would be coming from the sign of the second derivative. So concave down means f double primed of c would be negative. So the first derivative test, you're just checking to see where the sign of f prime changes. If f prime goes from negative to positive or from positive to negative, then the original function will have a min or a max. On the other hand, if you don't want to figure out the signs of f prime, sometimes it's easier to just look at the second derivative, just differentiate again and ask, okay, well, I've got a critical number, f primed of c is 0. I found that. Let me really quickly look at the second derivative there. If f primed of c is 0 and f double primed of c is positive, then that's got to be a local min, because that means I had a horizontal tangent line and I was concave up. On the other hand, if f primed of c is 0, horizontal tangent line, and f double primed of c is negative, meaning we're concave down, then that had to have been a local max. So this is our second derivative test. And it requires that your function be twice differentiable at c. That's the thing. So you need to be differentiable. You need to be differentiable again, and you want that second derivative to be continuous. So
the concave up and the concave down, those graph is belong to the second derivative.
So each of these graphs is the original function, but to figure out whether you are concave up or concave down, you would look at the second derivative. So if I had this function, if I had a formula for this function, and I differentiated it twice, I would find that that second derivative is always positive, and that corresponds with this being concave up. Does that answer the question?
Because when I read book, I don't remember you talk about the second derivative, but when I do the homework, I find the critical numbers, you only use the origin function and also the first derivative, because it get if from the first derivative to get the zero and get zeros, and also that has a close interval notation. So just put those critical numbers in the original function to get the absolute large maximum and the absolute minimum. But I don't remember you used for the I don't remember you used to the second derivative.
So some of what William is sharing is actually coming from a later section. So it's true that in 4.1, they don't talk about these derivative tests. And the main tool that they provide us here is this extreme value theorem and something called the closed interval method, which is here. So this is what Yiping's talking about, and it's a tool for finding absolute mins and maxes. William's looking ahead a little bit to section 4.3, which is how derivatives affect the shape of a graph. So it's true that if f prime is positive or increasing, if f prime is negative or decreasing, all of this is stuff that we're going to look at in greater detail later. The first derivative test is a nice way to talk about finding mins and maxes, but this involves a little bit of being circular. So he's just looking ahead. The second derivative test is what they say, sorry, concavity test. They talk about concavity here. And the second derivative test is something we'll look at in detail when we get to section 4.3. So don't panic if this isn't something that you've seen looking in 4.1. It is something that we're intending to talk about a little bit later, but it can help us understand what's going on in 4.1. For us, for now, the thing we want to focus on is really this. That critical numbers are places where the first derivative is either equal to 0 or undefined. And then we can use those to find mins and maxes. So if there's anything else that is a little bit difficult to follow here because we're pulling things from later sections, don't hesitate to ask. I'm happy to slow down and talk a little bit about them. All right, I'll move back over here.
So regarding points of inflection, yes, this is also moving ahead. Just a point of inflection, I believe, is like 4.4. But generally speaking, from when you have a relative max going to a relative min to a relative max, as long as it's continuous and differentiable and not throughout all of it, you will typically have a point of inflection at some points. This one's clearly defined. There's one right here, and there's one right here. But from right here, as this is concave down and this is concave up. Sorry, as this is concave up and this is concave down, there is always a point of inflection in between the two. And with that in mind, a thing I would like to show, just like on position, velocity, acceleration, or the f of x, f prime of x, f double time prime of x. You have your sine of x. This is increasing from up to here, and then decreasing from down here as up until pi over 2, and then if you take a look at the cosine, you have a cosine which is its prime, going from positive to negative at pi over 2. And in cases of points of inflection for sine of x, it's actually really easy to find, as it's a very consistent function. It's at it's from 0 and then every integer pi afterwards. would be a point of inflection, and that can be found through the double prime when that changes from positive to negative. More examples of this would probably be with x cubed, with x cubed, 3x squared, as I was showing earlier, and 6x. You have your position x cubed, or your f of x, x cubed. Then your prime had, in this one, it's actually quite interesting. There is no relative max there. And that's because x squared, while it hits 0, it doesn't actually cross from positive to negative. So there is no actual relative max there. What there is, though, is a point of inflection as it has 6x and as it goes from negative to positive. I believe the teacher went over this. Yeah, and I think that's about it.
Okay. Let's take a look at some examples where we do calculations, and let's try to keep them focused on just the tools of 4.1. So all of this stuff is very good, but I think it's going to take us some time to build up to those things. So what I would really like to do here is give ourselves a function and see if we can find mins and maxes. I want to remind you guys of a definition or two. So let's get the definitions and theorems that we need in here. First, we said this, but let's say it very, very clearly. The number x equals c is a critical number. Oops, sorry, it'll focus here. Give me 1 second. The number x equals c is a critical number for f of x if two things are true. First, f of c exists, right? C has to be in the domain. And f primed of c is 0. And implicit in that is that f is differentiable at c, right? Because otherwise we can't talk about what f primed of c is. And then a couple theorems. This is called Fermat's theorem. That is the same Fermat of Fermat's famous last theorem. It says, if f is differentiable at x equals c, and f has a local min or max at x equals c, then f primed of c will be 0. So in other words, critical numbers, places where the function's derivative is equal to 0, are a good way of hunting for local mins and local maxes, right? And these theorems are both in the textbook. Let's come up here. So local min, local max, definition, extreme value theorem, we'll get to that. So a critical number is a place where the function is defined, it's in the domain, and either f primed of c is 0 or, or f primed of c is undefined. Now, local mins and local maxes, we're going to talk about how to hunt those down a little bit more in future sections after we've understood better the increasing and decreasing stuff. But for now, what we're looking for are mostly absolute mins and absolute maxes. And the tool that we use for this, there's a theorem associated and a test, the closed interval method. So let me give these nice and clearly so we have them in our notes. So is called the extreme value theorem, and this is what William illustrated with those graphs. This says that any continuous function on a closed bounded interval will attain an absolute min and an absolute max. And it's important to think carefully about this theorem. Those were the pictures that, that William was showing us. The function must be continuous, and you must be looking on a closed bounded interval. But if you have those two things, then it's impossible for the function to avoid having both an absolute min and an absolute max. The tool that we use to find absolute mins and maxes comes from that theorem. This is the closed interval method. And it says to find the absolute extrema for a continuous function f on the interval, the closed bounded interval AB, we do the following things. First, find the critical numbers. Then find f of A and f of B. Then finally, compare the y values at the critical numbers with f of A and f of B. The largest of these is the absolute max. And the smallest is the absolute min. So in 4.1, we will find some local mins and local maxes. That's true. But because we don't have all the tools for classifying them and hunting them down yet, what we're primarily focused on are two things: finding critical numbers and finding the absolute min or absolute max of a continuous function on a closed interval. So let me grab an example here where we can do an actual calculation. Let's find the absolute min and absolute max for this function on the interval -1/2 to 4. So I'm going to write that function down, and then we can do the calculation together. So f of x here is x cubed minus 3x squared plus 1. And we're looking on the closed bounded interval -1/2 to 4. So our procedure is first to find any critical numbers. That means I need to look at the derivative of this function and ask, where is that derivative 0? Where is that derivative undefined? Then I will calculate the y value at -1/2, the y value at 4, and the y value at any of those critical numbers. Once I have all of those things, the largest y value is our absolute max, and the smallest y value is our absolute min. So my first step here is to compute f primed. F primed here is 3x squared 3x squared minus 6x. And I want to find where f prime is 0. So I need to factor this thing. And I can pull a common factor of 3x out. And what's left would be x minus 2. So f primed of x is equal to 0 when x is equal to 0 from this factor, or 2 from this factor. These are my critical numbers. Because f is a polynomial, its derivative is a polynomial. And polynomials are never undefined. So we don't have to worry about looking for places where the derivative is undefined. Let's just say that really quick. And f prime of x is never undefined because it's a polynomial. Just say polynomial. So that's my first step, right? Finding those critical numbers. I only have 2 of them. They are 0 and 2. My second step is to compute the value of the function at the endpoints. So that would be f of -1/2, which is -1/2 cubed minus 3 times -1/2 squared plus 1. The cube of -1/2 is -1/8, right? -1/2 times -1/2 times -1/2. The square of -1/2 is +1/4, so that will be -3/4, right? -3 times +1/4 plus 1. So if I have a common denominator here, that denominator would be 8. This is going to be -1/8 minus 6/8 plus 8/8, which is, where are we? 8 minus 6 is 2, minus 1 is 1,
1/8.
right? So this is, yeah, +1/8. The other endpoint is 4. So I'll compute f of 4, which is 4 cubed minus 3 times 4 squared plus 1. 4 cubed is 64 minus 3 times 4 squared. 4 squared is 16. 16 times 3 is, what is that? 48. And then plus 1. So 64 plus 1 is 65, minus 40 is 25, minus 8 is 17. My arithmetic correct there? 65 minus 40 is 25, minus 8 is 17. Yeah, okay. So we've got the values of our function at the endpoints. They're 1/8 and 17. The other thing we need here is the value of the function at the critical numbers. So f of 0 is 0 cubed minus 3 times 0 squared plus 1, which is 1. And f of 2 is 2 cubed minus 3 times 2 squared plus 1. So that's 8 minus, let's see, 2 squared is 4 times -3 is minus 12 plus 1, which is -4 plus 1 is -3. So now what we do is we compare all these outputs, all of these y values. F of 0 is 1. F of 4 is f of 2 is -3. F of 4 was 17. And f of -1/2 is 1/8. So the smallest of these is which one? -3, right? So that's our absolute min. And it occurs at x equals 2. So we have an absolute min at x equals 2, and the min value is -3. The largest of these is 17. So that's our absolute max. And he occurs at x equals 4. So this is the procedure for finding the absolute min and absolute max. What are these other things then, right? So at 0 and at 2, we had some stuff going on. F prime
Are they
of 0
relative?
was 0. So yeah, this is going to be most likely either a local min or local max, although it could also be an inflection point. And this guy was our absolute min. And because he came from a critical number, we can be confident that he's also a local min. Although at this stage, right now in section 4.1, you guys are not expected to know that. What you are expected to do is be able to come up with critical numbers and then find the absolute min and absolute max. And that's what we've done here. Let's take a look at this particular function in decimals. All right, so here we are, and we were restricting our attention to the interval -1/2.
We can't see the decimal screen.
Oh, weird. Sometimes this doesn't work right. All right, share screen. Share the whole screen. Okay, so in blue, we have this whole function, right, on its domain, which is -∞ to infinity. But they told us just to look at the function from -1/2 to +4. So here is the function restricted from -1/2 to +4. There's a bunch of stuff going on. The points we found were, let's do them one at a time, -1/2, 1/8. 4, 17. Those were the endpoints, right? This guy and this guy. The other ones that we found from our critical numbers were 0, 1 and 2, -3. Let's make all of these. Actually, tell you what. Yeah, whatever. Doesn't really matter, right? So what's going on? Well, when we found critical numbers, those were giving us these points. 0 and 2 were our critical numbers, and they did turn out to be a local max and a local min, although we're not required to have seen that yet. The other points that were interesting here were the endpoints, and those are always interesting. And it turns out that one of those endpoints provided our absolute max, while the other endpoint didn't give us shit, right? He was neither an absolute min nor an absolute max. And our absolute min came from one of those critical numbers. There may be, yeah, well, there definitely is an inflection point in here. It's somewhere right around here. Now, you don't need to worry about inflection points just yet. We will get there. But for now, inflection points are not something that you guys need to know about. So for now, let's focus just on finding the absolute min and absolute max and finding critical numbers. But it's true that somewhere around here is an IP. And if we wanted to find it, we would do that by taking the second derivative and seeing where that's 0. So my second derivative would be 6x² minus, or sorry, 6x minus 6. So yes, it's correct that there is an inflection point at 1. So again, for today, the thing I want you guys focused on is this closed interval method and finding critical numbers. So first we got to be able to find critical. Yes.
For the second part, why is it f of 4?
So remember what our closed interval method asks us to do. We want to first find critical numbers, then we evaluate the function at the endpoints. So because this is the closed interval method, we'll always be looking at a continuous function on a closed interval. And like we saw here, sometimes those endpoints don't give us anything, but sometimes those endpoints can be a max or a min. So what we were doing when we looked at f of 4 is computing this y value so that we could compare it to the other y values.
Oh, sorry, was 4 the y value?
4 was the x value. That was like our b in the interval from a to b.
Oh, I wrote that down as 9. Sorry. That's all.
That's my handwriting now. I apologize. But yeah, our interval here was -1/2 to 4. So in step 2, we computed the y values at those endpoints. And then in step 3, we compared those to the y values from our critical numbers.
Okay, thank you.
Of course. Let's take a look at one or two more direct computational examples. This is a good one. We're going to look at f of x equals x minus 2 sine x, and they want us to restrict our attention to the interval 0 to pi. And they're telling us to use a graphing device to estimate the absolute min and absolute max. We can take a look at that, and then we'll find them. So let's look at that function. So here's the whole function. Let me put this here. They want us to work from 0 to 2 pi. The whole function, you see he's got lots of critical numbers, right? Here, 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 here. Everywhere you have a local max or a local min, anywhere you have a horizontal tangent line, you're going to have a critical number. And because the sine function is periodic, we're going to have a shitload of them here. But they don't want us to look at all of them. They just want us to look at this portion. So what we're looking for are the absolute max and the absolute min. And the way we're going to find them is by using the closed interval method. So we want to find the absolute max and absolute min for f of x equals x minus 2 times the sine of x. So first we find the critical numbers. And I like this example because it requires solving a trig equation. Sorry, on the interval 0 to 2 pi. So first we find the critical numbers. To do that, we need the derivative. The derivative of x minus 2 sine x is 1 minus 2 cos x, which is never undefined. Right, because cosine's domain is all real numbers, and 1 minus 2 cosine, there's no other domain issues there. And f prime will be equal to 0 means 1 minus 2 cos x is equal to 0. You can subtract the 1 and you get -2 cos x equals -1. So cos x is +1/2. And everybody made it through our little skill test here. So everybody had to solve, I think, maybe this exact equation at some point before the start of the semester. Let me remind you how this is done. You look at your unit circle and you ask, where on this unit circle is cosine equal to 1/2? Well, here's cosine is the x values on the unit circle. Here's 1/2. So we're looking at this point and this point on my unit circle. The angle here is pi over 3. And there's two ways to think about this angle. You could think of it as negative pi over 3. But remember, I'm paying attention just to the interval 0 to 2 pi. So I would think of it like this, walking all the way around in the positive direction, because I can't be less than 0. What is this angle?
5 pi over 3.
Very good, 5 pi over 3. So first, all the solutions, which is true when x equals pi over 3 and 5 pi over 3. Now, these are not all the solutions to this equation, right? All the solutions to this equation, there's infinitely many, but these are all the solutions on the interval 0 to 2 pi. Because those are all the solutions you find walking around the unit circle in the positive direction once. So those are my critical numbers. We should compute f of 0. That's 0 minus 2 times the sine of 0, which is 0 minus 0, which is 0. And f of 2 pi, which is 2 pi minus the sine of 2 pi minus 2 times the sine of 2 pi, which is 2 pi minus 0, which is 2 pi. The other thing we need to do is compute the value of the function at those critical numbers. F of pi over 3 would be pi over 3 minus 2 times the sine of pi over 3, which is pi over 3 minus 2 times the sine of pi over 3 is the square root of 3 over 2. And f of 5 pi over 3 is 5 pi over 3 minus 2 times the sine of 5 pi over 3, which is 5 pi over 3 minus 2 times the sine of 5 pi over 3 is negative root 3 over 2. So this will be plus 2 times the square root of 3 over 2. So you can cancel the 2's. And here you get pi over 3 minus root 3. Here you get 5 pi over 3 plus root 3. And now we've got these 4 values to compare. So the question is, which one is the largest and which one is the smallest? And it's kind of hard to say, because how big is 5 pi over 3 plus the square root of 3? How big is pi over 3 minus the square root of 3? You want to do some either calculation here, and you can use your TI-30, or you can do some approximation. Let me show you some sloppy approximation. Pi is really close to 3, so 2 pi is really close to 6. Pi over 3 is pretty close to 1. So this is about 1 minus the square root of 3, 1.5-ish. So this is about negative 0.5. 5 pi over 3 is about 5, because pi over 3 is about 1. So this is about 5 plus 1.5-ish, or about 6.5. And 0, of course, is 0. So the largest of all of these is definitely 6.5, which is f of 5 pi over 3. So this is my absolute max. And it occurs at 5 pi over 3. all of these except for this one are positive. This is my absolute min. And it occurs at x equals positive pi over 3. And these other guys are local extrema. But again, we don't need to stress about that for now. We're just trying to identify the absolute min and the absolute max. And if we look back at our graph, this bears this out. So let me look at pi over 3, comma, pi over 3 minus square root 3. There it is. That's our abs min. And the other point that we found was 5 pi over 3, comma, 5 pi over 3 plus the square root of 3. So this is my absolute max. This time, the absolute min and absolute max were also local. Right? And there's no arguing that here because they're not endpoints. Even if you're being finicky about endpoints, these are both absolute and local. And the endpoints here were not terribly interesting. Right? In this case, neither endpoint was an interesting feature. So the closed interval method, that's the main thing I need you guys worried about today, finding critical numbers and the closed interval method. And we'll pick it up next time and elaborate a little bit further on some of the things William was saying at the start, like increasing and decreasing, inflection points, first and second derivative tests for local extrema. Those will be fun. But for now, keep your focus just on finding absolute extrema using the closed interval method. That will be our friend. Let's see, is there anything else we need to touch on here? I know we've gone a little bit over. No, I think we're good. So take your time finding critical numbers and take your time finding finding absolute extrema. And then we'll talk about local extrema and how derivatives play around with the shape of the graph next time. All righty.
Question, should we be able to do all the problems that are on the homework currently or just the ones for 4.1?
Just 4.1. Yeah, we haven't
Okay.
talked about the other stuff yet. So there are some things in there from 4.2. I haven't put anything in there from 4.3 or 4.4. So there's not any increasing, decreasing, or inflection point stuff in there. This week's homework is just these sections. 4.2 is on the mean value theorem, which is what I'll be talking about next time.
And which rough homework problems are going to be the 4.2 that we should avoid for the time being?
They should have, so there's a little number next to the problems that should tell you what section they come from, but I can, this will load. So you see here it says 3.10.002. That means that is the second problem from section 3.10. So if we scroll on down, critical number. Absmin. Oh, yeah, no, there isn't even any 4.2 on here. I haven't added the 4.2 problems yet. So everything that's in the homework right now, you guys can do.
Okay, thank you.
I didn't see the video from the Monday yet.
Okay, yeah, I can take a look and get that posted if it's not up yet.
And also, I want to ask which chapters will you teaching on the next semester? Which chapter will you teach on the next class?
4.2.
4.2, will you teach 4.3 and 4.4 in the future too?
Of course.
Okay.
Yep.
Thanks.
All right. Oh, and I did post the link for Monday's video. Is it not working? Ooh, something's gone wrong. Okay, I'll go back and take a look at that video because it should be up. I posted it, but for some reason YouTube says the video is still being processed. So I'll try to fix that. All right, guys, I got to get moving. I will see y'all next time.